Hi guys, welcome to lesson 4.5. 4.5 we are going to kind of change gears just a little bit here. We're still talking about solving quadratic equations. And so we're still looking at this idea of solving a quadratic. The only difference is that now we're going to use square roots. So we're not going to factor anymore. And we can get away with this because in the problems we're going to be solving, we're going to have something like, ax squared plus c is equal to 0. Generally speaking, there is no bx term, and I'll just say bx term, when you're solving by using square roots. All right, so just a bunch of definitions for you. We're going to be doing a bunch of work with radicals, and most of this should be kind of review for you, but sometimes we forget about, how do we simplify radical expressions and some of that kind of stuff. So we're going to spend a few minutes on some recapping and reviewing and talking a little bit about conjugates and some of that kind of stuff, and then we'll move right into the lesson here. So first of all, a square root is some number, a number r is a square root of a number s if r squared is equal to s. All right, and so for example, the square root of 25, we say that 5 is a square root of 25 because 5 squared is 25. All right, so there's one quick example. There are many more. A radical is an expression in the form radical s. It kind of looks like the old division sign, but it's a radical, and then where s is a number or an expression. It doesn't just have to be a number. It could be an expression like, 5x squared, for example. The radicand is the part of the radical expression that's underneath the radical sign. Now, rationalizing the denominator. We'll get more into this, but it says the process of eliminating a radical from the denominator of a fraction. Now, if you remember the term rational number, a rational number is one that repeats or terminates. Okay? It's when we get weird numbers like, 0.3869142, etc., etc. There's no pattern there. It's not repeating, and so this number would be an irrational number. Now, we get irrational numbers a lot from square roots. For example, take the square root of 6 in your calculator right now. Square root of 6 doesn't come out to a pretty number. That's an irrational number. So effectively, when I'm trying to rationalize the denominator, I'm trying to get rid of any radicals from the denominator or the bottom of a fraction. All right? And then finally, this idea of conjugates, expressions a plus radical b and a minus radical b. And we'll kind of talk a little bit more about this because this actually has a little bit to do with the sum and difference pattern, or in reverse, the difference of squares pattern. So we'll get into that a little bit more as we start looking at some examples here. All right, properties of square roots are as follows. First of all, the square root of a times b is the exact same thing as the square root of a times the square root of b. All right, so an example of that would be like, for example, the square root of 18 is the same thing as the square root of 9 times the square root of 2. Now, the square root of 9 does simplify. What is the square root of 9? Well, it's 3. And the square root of 2 does not. That's an irrational number, so we're going to leave it as 3 radical 2. So we can simplify, if we can simplify one part of that, we can say that's called simplifying a radical expression. The square root of some fraction a over b is the same thing as the square root of a over the square root of b. And so the square root of 2 over 25 becomes the square root of 2 over the square root of 25. Since I can take the square root of 25, that's 5, this becomes the square root of 2 over 5. And notice the denominator is rationalized, so we're done, and we'll get into an example of what that means in just a few minutes, okay? All right, so we want to very much familiarize ourselves with perfect squares. Before we can simplify some radical expressions, we kind of want to make a table and think about those perfect squares. And so things like 1, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on and so forth. I would really want you guys to be familiarize yourself with the perfect squares all the way up to maybe 15 or potentially even higher. I mean, the more perfect squares you know, the easier your work is going to be. And then, like I said, there are plenty of them in between. So I want to write 24 as the product of two numbers where I can take the square root of one of them. Well, to take the square root of a number evenly, it has to be a perfect square, right? Well, 24 is the same thing as 6 times 4, isn't it? Well, that means I can write this as the square root of 6 times the square root of 4. Now, the square root of 6 doesn't simplify, so I'm going to leave that as the square root of 6. But the square root of 4 does. Square root of 4 is 2. And so the square root of 24 can be simplified as 2 radical 6. All right, so as far as notation goes, again, when we read this, instead of saying 2 times the square root of 6, we simply say 2 radical 6. Okay. All right, what about the next one? This is the square root of 5 times the square root of 18. Well, the square root of 5 times the square root of 18 is the same thing as the square root of 90. So let's think of factors of 90. Is there a factor of 90 that's a perfect square? Well, for some of you guys that are quite astute at this and very good at recognizing factors, 90 is the same thing as 9 times 10. So what is the square root of 9? Well, that's 3. And then the square root of 10 doesn't have any factors that are perfect squares. Again, think of the numbers that could possibly go into 10, like 9 and 4 and 1. Well, certainly 1 goes in there, but that's not going to do us any good, right? All right, so for letter C, this becomes the square root of 9 over the square root of 64. Like I said, we get to separate it into two separate radicals, and the square root of 9 is 3, the square root of 64 is 8, and so the square root of 9 over 64 is the same thing as 3/8. All right, so let's take a look at doing something called rationalizing the denominator. All right, now the first piece of this is I have the square root of 7 the square root of 7 divided by 3. Well, that's the same thing as the square root of 7 over the square root of 3, or radical 7 over radical 3. So if I want to get rid of the radical 3, to rationalize the denominator says to get rid of any irrational numbers in the bottom. Well, the square root of 3 is not, it's equal to like 1 point something or other. It doesn't come out to a very pretty number, all right? So that's irrational. So if I could multiply this fraction by effectively the number 1, then I could eliminate the square root of 3 on the bottom. Well, I'm going to choose to multiply both top and bottom by the square root of 3. Now, first of all, these two numbers on top and bottom have got to match exactly, because effectively, again, what we're doing is we're really multiplying by 1. Anytime you have a number over itself, it's 1. So the square root of 3 over the square root of 3 is 1. Now, why did I choose the square root of 3? Well, on top, I'm going to get the square root of 7 times the square root of 3, which becomes the square root of 21. On the bottom, then, I'm going to get the square root of 3 times 3. Well, the square root of 3 times 3 is the square root of 9. Well, isn't that then simply 3? And so when I do radical 3 times radical 3 times radical 3 is radical 9, which is 3. All right, 4 over 5 plus radical 3. Okay, we can't simply multiply top and bottom by radical 3, because if I did that, like we did in the previous problem, I would have to distribute, which would get rid of this radical sign, but I'd still have 5 times radical 3, which is going to make a mess of things. Instead, what we use is we use something called the conjugate, all right? And the conjugate of this is 5 minus radical 3. And so I want to multiply both top and bottom by 5 minus radical 3. Now, you might be asking yourself, why am I choosing 5 plus radical 3 times 5 minus radical 3? What's the point of that? Well, if you remember from the sum and difference pattern, when we talked about foiling something that has the exact same thing in these two spots, the exact same thing in these two spots, where one is a plus and one is a minus, that middle term is going to cancel out. Now, if you don't believe me, 5 times 5 is 25. And then 5 times negative radical 3 is negative 5 radical 3. Radical 3 times 5 is plus 5 radical 3. And then on the end, you have plus radical 3 times negative radical 3, which becomes negative radical 9. All right, we'll simplify that in just a second here. So what happens with negative 5 radical 3 and positive 5 radical 3? Well, those just get to cancel each other out. And then I can actually do radical 9, that's 3. And so on the bottom of this thing, I simply end up with 25 minus 3. Okay? On the top, we have to distribute. So we have to do 4 times 5. And then, since I used minus, this is minus 4 times radical 3. Now, 4 times 5 is 20, minus 4 radical 3. So the top is done. And on the bottom, 25 take away 3 is 22. Now, I know what you're thinking. This is not any simpler than this. But the key about this one is notice the denominator of this fraction. Is it a rational number? Well, yes, the number 22 is a rational number because it doesn't include any square roots. All right, so let's go ahead and see if we can't work through a couple of checkpoint problems. Try these, pause your video, try these two examples, and we'll be right back with solutions. So I can write the square root of 5 times the square root of 10 as the square root of 5 times 10, which is the same thing as the square root of 50. Now, I'm thinking about my perfect squares. Okay, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. 5 squared is 25, right? So if 5 squared is 25, that says that 25 is a perfect square. Notice that 50 is the same thing as 2 times 25. So I can write 50 as the square root of 2 times the square root of 25. This is radical 2 times radical 25. And guys, what is the square root of 2? Well, that's not pretty. So we're going to leave that as radical 2. But on the front side, we're going to move this out front. What is radical 25? Well, the square root of 25 is 5. And so this is 5 radical 2. What about number 2? Number 2 is the same thing as radical 9 over radical 11. All right, that does not simplify very well. And so what I want to do is I want to multiply both top and bottom by radical 11. Now, we're multiplying by radical 11 over radical 11. This is the same thing as the number 1. So if I multiply top and bottom by, the same thing, I'm essentially multiplying by 1. On top, this is radical 99. On bottom, this is radical 11 times radical 11, which becomes radical 11 squared, or radical 121, however you want to look at it. So the square root of 121 is 11, so the bottom simply becomes 11. On the top, 99 is the same thing as 9 times 11. So the square root of 9 is 3. The square root of 11 stays underneath, and we still have the 11 in the denominator. Again, this is a rational number downstairs, so we are complete. So what does this have to do with solving quadratic equations? Notice that there is no bx term in this particular problem. And so, again, this is actually something written more like in vertex form, which really, we haven't done much with solving something like this. But my original equation says 1/4 y minus 6 squared equals 8. So if I multiply each side of this thing by 4, I get 32 over here, and I simply get y minus 6 squared. Now, forget about the fact that this says y minus 6. This says something squared is equal to 32. So how do I get rid of squaring something? Well, the opposite of squaring is taking the square root. And so when I take the square root of y minus 6 squared, I simply get y minus 6. On the other side, I get the square root of 32. Now, there are two numbers I can square and get 32, positive 32 and negative 32. All right? So at this point, I have plus or minus radical 32. From there, I'm going to add 6 to both sides of this thing. Now, I like the 6 to be in front, so this is 6 plus radical 32. All right, now 32 underneath the radical sign, let's think about 32. Okay, 32 is the same thing as 2 times 16. Now, again, you're not going to be real good at this initially. Okay, you've done this long enough, you kind of know what numbers are perfect squares that evenly divide into others. And so the factor of 32 that's the largest that's a perfect square is 16. So this becomes the square root of 2 times the square root of 16. Square root of 2 doesn't simplify, but the square root of 16 is 4. So this is 6 plus 4 radical 2. Oops, I'm sorry, plus or minus, plus or minus. So this is 6 plus 4 radical 2, 6 minus 4 radical 2. Now listen, you can get an answer in your calculator, and it's going to be something decimal related because of this irrational portion of your answer. Those decimal answers will be marked incorrect. You have to know how to simplify the radical expression. All right? So let's talk about a water balloon. Okay, this actually has something to do with something called the vertical motion model. The vertical motion model says the height of some object dropped from a specific height with no initial velocity is negative 16t squared plus h sub 0, where h sub 0 is the original height. In this case, it tells me the original height is 59, and I want to know when does it hit the sidewalk. Well, what's the height of it if it's on the sidewalk? Here's my water balloon, here's the sidewalk, I drop it, and so the height of that thing is equal to 0. So I want to know at what time will the height equal 0. So I substitute in 0 for height and 59 for the original height of the object I'm going to drop. Now, I'm going to subtract 59 from both sides. And so this becomes negative 59 is equal to negative 16t squared. Divide both sides by negative 16. We don't have to worry about snip method or anything like that because we've got no bx term. There's no x to the first power, in this case t. And so I get negative 59 over negative 16, which becomes positive 59 over positive 16. And so this becomes roughly, I'll just leave it as 59 over 16 like that. So we're going to subtract the 59 from both sides, divide both sides by negative 16, and then to get rid of this now becomes t squared equals 59 over 16. To get rid of the square, I'm going to take the square root of both sides. And so, guys, you don't have to worry about simplifying this in terms of a radical expression because we're looking for an approximate time. If I told you the time was 2 plus the square root of 3 seconds, that would make no sense to you. And so I just I'm going to go ahead and give this as a decimal. This is then plus or minus 1.9 seconds. Now, obviously time can't go backwards, so the negative is not even an option. We just simply want to consider the positive 1.9 seconds. and so my time then is approximately 1.9 seconds. All right. We obviously reject the negative solution, the negative 1.9, because in this case, time's got to be positive, so the water balloon is going to hit the ground in about 1.9 seconds. Try the 2 checkpoint problems down below, and we'll be right back with solutions, guys. All right, so for number 3, we've got to get all of our x squareds on one side and all of our constants on the other, so I'm going to add 16 to here and here. I get 2x squared is equal to 50, and when I divide both sides by 2, I get x squared equals 25. Now this one actually kind of works out pretty slick, because when I take the square root of both sides, x is equal to both positive and negative 5. Okay, don't forget to consider plus or minus when you take square roots. There are 2 numbers I can square to get 25. They are positive 5 and negative 5. And if you remember that, that will serve you well for our next lesson as we start talking about pluses and minuses. All right, in example number 4, again, we want to know when does it hit the ground. It's negative 16t squared plus the initial height of 27. Okay, I'm actually going to add the 16t squared to both sides because I'd rather have my variables be positive. This is then 16t squared equals 27. Divide both sides by 16, and you get t squared is approximately, I think it's 1.6875 or something like that. 6875, yep. And then when I take the square root of that, I get t equals plus or minus 1.2999, et cetera, et cetera. Okay, so we can pretty much call that 1.3 seconds. Again, we can reject the negative possibility because time can't be negative. So we're going to say time is approximately 1.3 seconds. So at about 1.3 seconds, that water balloon will hit the ground from a height of 27 feet.